This presentation will focus on the Compton effect. The Compton effect is one of four possible interactions that occur when radiation leaves the X-ray tube and subsequently interacts with matter. This presentation is narrated by John Toman. To begin this discussion, we will start with the nucleus of an atom. But since the nucleus is not relevant to this discussion, let's move away and view the atom from the perspective of the electron shells. Here we see a representation of an atom with its electron shells included. Only shells K through L are illustrated for the sake of simplicity. Off to the right, a small blue circle with a P inside represents a photon of X-ray energy. Before I begin the animation, be aware that Compton interactions will most likely involve loosely bound outer shell electrons, and since these electrons are more numerous than others, they have a high probability of interaction. The interaction overall is fairly simple. The photon speeds towards the electron shells where it strikes an electron. From this point, I often characterize this interaction as a pool ball reaction because the electron is ejected from its orbital and the X-ray photon continues its travel in a new direction with less energy. Since the photon has been diverted from its original path, it is now classed as scatter radiation. Scatter is the radiation that lead aprons and gloves are specifically designed to stop. Due to its random nature, scatter radiation is also responsible for the creation of fog if captured by an image receptor. Since this dislodged electron has a lower binding energy, the photon didn't use much energy to knock it loose. The resulting scatter may still have a large amount of kinetic energy and therefore has an increased probability of leaving the patient and interacting with things and persons outside the patient's body, so that it can be correctly said that most radiation leaving the patient's body's tissues are caused by Compton interaction. This slide summarizes the Compton interaction. One can see the incoming photon and the resulting scatter radiation. One important characteristic of a Compton interaction is that the higher the energy of the incoming photon, the more likely the scatter is to exit the patient and more likely to be directed towards the image receptor. This accounts for the fact that higher kV techniques typically produce more fog on the image receptor. Here are some points you should know about Compton radiation. Where photoelectric interactions are responsible for secondary radiation, Compton interactions are responsible for scatter radiation. While many technologists use the terms scatter and secondary radiation interchangeably, most of the radiation exiting a patient during an examination is produced by the Compton effect and is most properly called scatter. During an interaction, the initial X-ray photon loses energy due to the fact that it transfers some of its energy to the electron that is dislodged, and due to that fact, it also has changed direction. Since the scatter photon has less energy than the primary radiation, it can be easily stopped by lead garments. Finally, my last 2 points at first glance seem contradictory. As with all forms of attenuation, the probability of interaction decreases with the energy of the primary beam. Higher energy radiation is always more penetrating and less likely to interact with patient tissues, and the Compton radiation, the story is no different. Where things seem contradictory is the statement that high kV exposures will produce more fog on the image receptor due to an increased presence of scatter radiation. This situation results from the fact that high kV exposures produce a scatter photon that is 1, more likely to exit the patient, and 2, more likely to be directed towards the image receptor. This will end my presentation on the Compton effect.